Thank you for coming to my presentation. I'd like to use this opportunity to tell you a little bit about this new statistical model that I'm proposing. And this is for the modeling of biological feedbacks. Okay. And I try to minimize the mathematical derivation and equations, but there are still a few there. And if you don't want to look at the Greek letters, don't look at them. And I will try to tell you the idea behind the equations. Okay. So we're talking about statistical models. What is a statistical model? I mean, depends on who you ask, but my own definition is statistical model is just a tool that allow you to link a set of independent variables with certain outcome. Okay. Now, an important part of the statistical model is the model ought to be built on the observed data so that to some extent it will be able to imitate the behavior of nature. Even though we may not know the precise biological mechanism driving the relationship between X and Y, we were able to get something very close to it. So we would get something close to what nature would produce. That's the whole idea of statistical modeling. What you see here on the screen is a regression model. Y is the outcome, X is a vector of the independent variables, and epsilon is the error term, which tells you the amount of uncertainty associated with the model. Okay. So this simple structure actually is the foundation of most of the advanced statistical models. I list a few here, and when I forgot to list the algorithm-based models. So those are the neural networks and machine learning approaches, but they all have regression as a component embedded into the model. Now, when we look at such models, we ask ourselves, so the model has been very useful, has been here for over 200 years, and we use them all the time. But is there anything else to be desired from such a structure? I would say one thing that is very obvious is such model only describe the unidirectional effect. In other words, X influences Y, but Y does not influence X. Is that reasonable? Well, in some contexts, maybe that's okay, because you're just looking at a fraction of a biological system. But when you look at the system as a whole, that is not the right view. And this is a severe limitation because we know that biological feedbacks are very important in any biological system. Like in human body, if you don't have these feedbacks, you would not be able to maintain homeostasis. And in other biological systems, without feedbacks, you would not be able to achieve the steady state relationship you try to describe. Okay, and this is not only restricted to biology, can be any other type of applications. I mean, even you think about human behavior, it has a certain feedback type of characteristic. For example, many people here in this room study medication adherence. We promote medication adherence. And when people do adhere to their prescribed medication, their clinical outcome tend to improve. But when the clinical outcome improves, well, some patients may feel, not all of them, some will feel, maybe I don't need to take the medication anymore, right? That kind of have an impact on the adherence. So there are many examples. This is one example I'm going to come back to a little bit later. This is a part of the renin-angiotensin-aldosterone system. I have been studying hypertension for many years, and the focus of the work is about aldosterone and its role in blood pressure regulation. So I'm just picking up this as an example. But if you think about, by the way, for people who don't already know, aldosterone is a mineralocorticoid hormone. It acts in the on the epithelium sodium channel in the collecting duct of the kidney to upregulate sodium retention. Okay, so if you think about how aldosterone is produced, there are two important factors here. One is angiotensin II. Of course, we can't measure angiotensin II usually, so we measure plasma renin activity to approximate angiotensin II. The other is potassium. Now, in the absence of potassium, actually angiotensin II will lose its function in aldosterone production. Okay, but when aldosterone is high, it tends to help to more efficiently dispose potassium. So you see the feedback effect here. Okay. All right, so what does it take to model a biological feedback or feedback loop? Well, some people may say, well, I can switch X and Y. I can make X the dependent variable, Y the independent variable. Would that work? The answer is no. If you are observing, let's say come back to the renin and aldosterone example, the two different chemicals are measured from the same blood sample. So all you are observing is some sort of association because you're measuring them together. There is no way you can tell whether this is the influence of renin on aldosterone or aldosterone on renin. You get two different numbers, but they are two different numbers to quantify the strength of that association. So with that in mind, clearly cross-sectional data would not work, okay? And so what you need actually is a dynamic system that try to mimic the behavior of this biological system. You could do it with observational data, but the time of observation has to be very well chosen so that you actually see the effect, you capture the feedback effect, okay? There are a number of other things that you have to deal with in such models. One of them is the nonlinear effect, and also the second thing is there are usually multiple components in a biological system. So it's going to be an equation system instead of one model, one equation for a simple model. And also all these different components may interact with one another. And that creates a lot of difficulty in the modeling exercise. This part I'm going to skip very quickly. What we are trying to do is to come up with some model that simultaneously capture the nonlinear interactions. And so what you see here, Y1 and Y2, these are just two different components in a system. So you can consider them to be the outcomes. U and V are the other factors. And we model U and V's effects on Y1 and on Y2, but we do not specify what type of association it is. So we leave it as a function. We're trying to use what we call non-parametric methods to estimate these functions. Okay, that's all I think I need to say about this. And there are a few other slides. But the bottom line is we are able to capture the nonlinear interacting influences in a biological system. The only thing we're missing in this picture is the feedback, okay? So this is the feedback model that I'm putting forward. Here in the system, I have K elements that I want to model, or you can think of them as K components. And at each time point, I measure these K different components. And so starting from time 1, that's the baseline. And at time 2, I actually can see how Y2, Y3 up to YK influence Y1, okay? And then I can do the same thing for Y2 and the same thing for YK. The feedback is actually what you will see starting from time 3. So that you can see again, Y1 is now influenced by Y2, Y3, and YK. So this way, you actually have an equation system that captures the dynamic over time about the interaction of these different models. For each line here, essentially we're trying to do is to fit a nonlinear, we're trying to fit a nonlinear model. That's the semi-parametric model I just showed you. So together, this is could be a very complicated model. So let's come back to the example that I have been using, that's aldosterone, potassium, and renin. Here, the first equation is for aldosterone. So we're modeling the aldosterone as a function at the time t as a function of renin and potassium at a previous time point. So this way we capture how it affects the aldosterone. And then for potassium, we actually model it as a function of aldosterone and renin, and so on and so forth. You can make the model as complicated as you want. You can add additional components to it. But this is the idea, okay? Now, what I want to spend maybe maybe 5 minutes on is actually how we fit such a model. I mean, the model is not so difficult to write down. It's a little bit typing, but it's not so much. But one thing I want to tell you is if you try to fit the model using the frequentist approach that we have developed in regression and advanced regression models, I would say good luck. It won't work. Why? Because the number of parameters. There is a huge number of parameters because we have these nonlinear functions, we have the feedbacks, and we have this dynamic structure. And I will give you an example later on. So how about MCMC, the Bayesian approach that many people rely on when they run into difficulty with computation? Well, I would say I'm actually going to show you a little example, animation that show you that can be very, very slow. The reason is this: think about a simple situation. We're living in this three-dimensional space. So we have the latitude, longitude, and the altitude, right? If this is where the true parameter is, or the center of the parameter, the probability mass is, and you start somewhere, and you just randomly walk around, which is MCMC is doing, how long does it take for you to hit this point? Pretty long time, even with fast computers. Now think if you have a space, if you're working in a space with 100 dimensions, what will happen? That's almost impossible. So we need some tools to help us get to the area fast. And this idea actually is from physics. For particle physics and quantum physics, they have a tool. That's called Hamiltonian equation. I won't show you the details of the method, but I will quickly tell you what the idea. So suppose that there are two panels. I'm looking at the top panel. This is the posterior distribution. That's what we care about in Bayesian data analysis. What we are trying to do is to simulate data following that distribution, okay? And if you like to work with the inverse log of that function, it would be the bottom curve, okay? So what we want to generate data are, we want to generate data points somewhere in the middle, okay? And overall, when we generate data, lots of data, hopefully it's recaptured this distribution. That's the idea. So for one-dimensional case, if you just randomly simulate numbers along this line, that's not so difficult. But think about this high-dimensional space. That's almost impossible. So we need some guidance to take us to that area of interest, okay? And what we do is, I think is a really a genius approach that I always have the highest respect for physicists. I mean, they come up with all these brilliant ideas. And think about this curve. Here I have 4 panels. It's the same curve, okay? Think of this curve as the inverse log of the posterior distribution, okay? And what we want to do is to generate data that simulates basically the distribution of this curve. So imagine that we have a ball and we give it a push. And let's say push in this direction. So we give it a little bit momentum. So when we kick the ball gain what we call kinetic energy. So that the ball will go uphill, okay? And gradually the speed will reduce. And finally it will stop. Stop at this point. So all of the kinetic energy is gone. What happened? All of the kinetic energy now is turned to potential energy because of gravity. So this ball will rolling back again, okay? And then it hits the bottom, and that's when all of the potential energy is turned to kinetic energy. But it will continue to roll uphill on this side. So you can think if it is really a frictionless surface, this ball will keep doing this. So if you can sample the track of the movement, then you basically mimic this function. That is a brilliant idea. Or at least I thought it was pretty amazing. So the equations that governs the conversion between kinetic energy and potential energy are these differential equations. So this is essentially, you can solve the differential equations to guide you how to approximate the surface, okay? Now remember, here we introduce something else. That is called a momentum. What is that momentum? That is that random kick we gave to the ball, okay? And so that is, momentum is P here. So we're not only considering theta, the parameters of interest, we are also considering the momentum associated with it. And the momentum is generated from a random process. So, but anyway, we need to solve the differential equation system. These are partial differential equation system. If you have a high dimension, it's going to be a high dimensional differential equation system. So there is no free lunch. You still need to do something. And how do we solve the differential equation? For those who still remember the days of calculus, and we use Euler's method, right? But Euler's method tend to accumulate the error. This is the trace of the Euler's method, you know? So if this is the true trace, the target trace, this is a true function, and your Euler's approximation tend to get further and further away because the error accumulates, okay? Now, so there were modified Euler's methods, and this is where the mathematician and a computer scientist talents come into help. So they developed this program called leapfrog algorithm. So it's like a jumping from point to point. It depends on how far you jump. You still bound by this Hamiltonian equation so that it approximates this true function, okay? But anyway, those are the technical details I won't spend too much time talking about. And let's just show you an example. So here we are looking at this example. I'm looking at the association between aldosterone, potassium, and renin. And the data actually come from a clinical study. It was an experiment to evaluate the loop diuretic effect of the sodium potassium 2 chloride co-transporter in the thick ascending limb. So this is the other site where fluid and sodium got absorbed in the nephron. Okay, so we have 199 healthy subjects, and basically we get them standardized diet and let them stay in a clinic for the whole night. And then we gave them, in the morning, we gave them furosemide, which is a loop diuretic. And of course, the furosemide will wipe out the whole activity, wipe out the fluid volume completely. But so what I'm showing you today is just before you gave furosemide. Okay, I'm sorry, furosemide. It's before. And after you gave the furosemide, there is it's just a complication. So for my purpose, just showing the model, I just gave you the time before. So the three players are plasma renin activity, plasma aldosterone concentration, and urine sodium excretion. And here we are able to use urine instead of plasma. We're using, instead of plasma potassium concentration, we're using urine because I think the measurement was done more accurately. And the reason we could use urine was because they are on standardized diet. So we know what they take in. So we're just thinking what they get out. Here's the model. This is a very simple model with only three outcomes. And here, for example, aldosterone was modeled as a function of plasma renin activity and potassium with other things. So if you look at the number of parameters, we have 5 fixed effects. These are the race, sex, and BMI, and age, all these. We have 5 parameters, but we have 3 outcomes, so that would be 5 times 3. And we have a large number of random intercepts. I mean, we don't count them as all of them as parameters because they are generated from a mechanism. And there were 50 knots for each of the smooth surface. And now you think with 3 outcomes, that's 150. And so anyway, the point is the dimension is really high. And if you're trying to use a likelihood-based method to estimate it, all I can say is good luck. So let me first show you the results. So this is what our model produced as the predicted value versus what we actually observed. So this is the aldosterone level. This of course is way better than I expected. It's really worked well for prediction. But not always. Some of the outcome you will see not working as well. And this plot is the simultaneous effect of the plasma renin activity and potassium on aldosterone level. So potassium and renin were measured at a previous time point, so basically an hour ago. And we're looking at the current time point, what's the aldo level. So looks like the higher, the red color indicates a higher level, blue color indicates a lower level. So you can look at this, you would say, oh, this is primarily driven by renin, which is the case, it's true. I mean, I think we expect this. But of course, you can't do this without potassium. But who would be without potassium? I mean, we have a very tight range for our plasma potassium level. Outside of that level, you're gonna have trouble living, right? And so this is the kind of model that we can do. Of course, you can also look at the same thing for renin, okay? And for potassium, this is where we actually got into a little bit. You look at there is vaguely a trend, but not as clear. Okay, this is, of course, we know that urine potassium excretion or any urine electrolytes excretion tend to vary quite a bit. I mean, there are all these factors that, for example, your creatinine level and all these. So we think this is acceptable. although, you know, could be better, but still overall, I think we're pretty happy. Now look at this. So this is the feedback actually. When aldo is high, looks like you get more potassium out of the body. Why? Because you're taking in more sodium in exchange for potassium. So this is how we think it makes sense. Okay. There is a whole, I don't have the time to tell you that, but there is a whole background, scientific background, and you know, it's quite interesting as well. So just to end this presentation, I would say, now we have put forward a model that simultaneously assesses both the feed forward and the feedback effects of multiple components in a biological system. And I like to say, or I like to think, that the same model can also be used to model the feedback loops in other type of applications. I don't necessarily think it has to be so biological. I just haven't had the opportunity to try that. And what you want actually is some sensibly chosen observational intervals. And the biggest challenge, I think, is the computational issues. You have to deal with the computation. So when you look at the model that, if you look at this model, I want to tell you why I think of this idea. When you look at this model, initially, some people say, I showed it to a friend, he says, is this neural network? I said, no, it's not, but it looks like a neural network. The difference is neural network doesn't give you the feedback. It have all these layers. You dig deeper and deeper. It's always feeding forward. It's not feeding backwards, but we have both forward and a backward. And then I started looking at how people fit neural network models. Of course, you use gradient descent and all these great methods, but then I realized in the early literature, especially when the physicists start getting involved, they use Hamiltonian Monte Carlo. That's how I start to think, okay, this is, but anyway, this is pretty much my presentation. Let me, so we're currently developing a computational software for a broad class of applications so that people can run it. And I can tell you that this model takes about a few minutes to run. And if you use traditional Monte Carlo MCMC, it takes days and it still doesn't converge. That's the difference. So with that, let me just show you a quick animation. So this is a comparison between the MCMC, the traditional MCMC, random walk metropolis Hastings algorithm, and the Euclidean Hamiltonian Monte Carlo. So this one is HMC, that's Hamiltonian Monte Carlo. This one is metropolis Hastings. The parameter is here, okay? It's called alpha. And here, because remember in Hamiltonian Monte Carlo, we also have a momentum. So the momentum is another added dimension. And these are the trace plots. You will be able to see which one converge to that center point faster. Let's run it. See the trace plots here? It's still wandering around. And this, you basically hit there so quickly. And for those who do Bayesian data analysis, you look at the trace plots. This converged, Hamiltonian Monte Carlo converged very fast. It mixed well. It's a well-behaved stationary Markov chain, but not this one. This one takes a long time to converge. But this is a simple application, so both converges. Okay, all right, that's all I'm gonna say.